This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, now I will switch over so you can see me. So welcome to medical imaging, home isolation style. As you can see on the screen, essentially the way we've set up the lectures is to keep microphone and video off because not everyone has great internet. If you're on a computer and you press the space bar, that will temporarily unmute you. And so if I'm asking a question and you know the answer and you want to give it a go, feel free to do that. As soon as you release the space bar, then you'll be muted again. So instead of having to click back and forth, that's an easy way to do it. The other option is to use the chat box, and Manuela, who some of you have heard me chatting to, is a PhD student in the group, and she is basically here just to help. So you can send messages to her and she'll send them to me if I'm not responding fast enough to one of your questions. So in your settings, you should be able to see like a little hand raise icon, so you can use that to raise your hand. I can't seem to see it right now, but I'm sure it's here somewhere. And yeah, there's also a yes, no. So if you want to, you don't want to actually have to use your voice, you can use that to answer some of my questions. Expect that there will be some sound and video artifacts. It's one of the joys of being on the National Broadband Network or similar. And so we just have to be patient. And if we lose connection for some reason and I can't get the meeting restarted, which is essentially what happened last week, then just go straight to Canvas for any announcements, as in a new meeting ID or a plan for what happens next. So anyway, this is fun. So for those of you who were on earlier, you would have seen I have been trying to make a virtual campus work for me in the comfort of my own house. And so for your viewing pleasure, this is my new doc cam. So this is sitting just to the right of me. Here we have the document. We have the webcam, which you can see I've got perfect. It's exactly 5 Lego studs wide. So it fits perfectly into its new housing. And there's a light that I've got there to help keep the page lit. This is the best of the bunch that I could find for you. And then you can see the whole unit for my technician. Basically, it's tall enough to make sure we've got everything on the page, but be aware there's no zoom. So unlike a regular doc cam, I can't actually get closer or further away. So I've tried to pick the perfect height that kind of gets enough on the page without me having to move it up line by line. You'll also notice it includes an infinity pool, an open air bedroom for our techie, a ladder for cleaning the camera so you can climb down and get to it, a balcony with a telescope so you can keep an eye on things down at the page level, and also a fearless technician because you need somebody who's happy to come to the edge of a building that's that much taller than he is. Anyway, so that's what I've got working for you. So I've got the ability to switch over to another camera and you're not looking at me, but you'd be looking at the technician and the page that he's looking at. So I'm going to stop that share and I'm going to bring up the tutorial sheet. So bear with me while I make this work for us. I'll bring up my share again. Come on. There it is. So that is this one. So you guys should have access to this as well on Canvas. And that's been there for about a week now. So I hope you've had a chance to look at it. And I'm just going to work our way through it. I want to get through as much of this as we can today. What we don't get through today, I will put the solutions up and you should be able to work through the rest in your own time. If you've got questions, just shoot me an email and we can work it out. Yeah. So let's get started. The first question says, Figure 1, which is this whole figure that you've got down here, shows the intensity of X-rays, so that's our y-axis, produced by a source as a function of their energy, which is our x-axis. And it says, with respect to the reference graph shown on the left, so this one here is our reference, one plot corresponds to a decrease in tube current and the other to a decrease in the accelerating voltage, the kVp. And so they want to know, of these two plots, this middle one and this one on the right, which one corresponds to a decrease in tube current and which one corresponds to a decrease in accelerating voltage. And so I guess my question to you guys is, does anyone want to have a go at answering that question? Like I said, you can either unmute yourself with the space bar, or you can type something into the chat box. And I'm going to shift over to DocCam mode. So, I don't know how to pronounce your name, I'm sorry. You're saying the middle one for the lower current. So this one here is less current. So what would be the thinking there? Yeah, okay. So your characteristic radiation are these spikies here. And so what would who remembers we had a slide, I think it was about number 25 or so, according to my notes, it might be slightly off, that said that our intensity was proportional to kVp squared multiplied by milliamps. And we said kVp squared was the energy of the X-rays, that's our kVp, and our milliamps is the number of X-rays. So if we've got a decrease in the number of X-rays, then we can essentially be saying that we're having fewer electrons actually get to the anode. And so if fewer electrons get to the anode, that means I'm producing fewer X-rays. And if I'm producing fewer X-rays, then I'm going to have a less intense beam. Does that make sense? So then essentially so we're saying decrease in tube current means that this y-axis is basically decreased from here to here. Okay, so the spectrum looks the same, but the intensity is decreased. So then the other half of the question is a decrease in accelerating voltage. So basically we would say that one belongs here. Can anyone describe for me why this shape would be the result of a decreased accelerating voltage? No one's brave enough right now. So essentially what we're seeing is I'm going to get a lower energy spectrum because I don't have as much, my accelerating voltage has only got, say, up to 70 kVp instead of 150. And so as that decreases, it means that the maximum energy that I can get for my beam is also going to be reduced. And so essentially that comes down to the same equation, that intensity is proportional to kVp squared multiplied by current. So moving down the list, the second problem here has got the same spectrum that we just saw, and it says the spectrum of X-ray energy changes as X-rays pass through a tissue due to the energy dependence of the linear attenuation coefficient. So this was our mu value. So they're saying the spectrum of energies changes as it passes through the tissue. And this is a phenomenon known as beam hardening, which we haven't really talked about in any detail yet. But they're asking us, so this is what comes into the body. And then if you look at the energy spectrum on the other side of the body, what would it look like? How would this spectrum change after it's passed through the body? Has anyone got any ideas there? So what would you say about the high energy X-rays? Would they get all the way through? Nobody? Yes, we would see most of the right-hand side of the spectrum. So you reckon we will still see this? What are we going to see over here at the left-hand side? What would happen there? What happens to those low energy X-rays? Got one engaged student. Come on, guys. Feel free to unmute yourself and use your words. Yep, so what do we mean by the photoelectric effect? Essentially, the body is going to absorb that energy, and so what's going to happen is we're going to kind of drop off, and so we lose those. That just gets absorbed by the body, right? Is that what you meant, Mitchell? Yep. Excellent. So yeah, so basically that's what we're seeing is the body is absorbing those low energy ones. They don't have enough energy to get through the body, essentially. Let's keep moving, making good time. So in figure 3, which is actually at the bottom of the next page on the left-hand side, it says calculate the X-ray intensity. So this is I as a function of the incident intensity, I0, that reaches the film for each of 3 X-ray beams. And so if you look down at the bottom of the page here, we're focused on this panel here, and we've got 3 X-ray beams passing through one material that has 1 dark grey and 1 centimetre of dark grey and 3 centimetres of light grey, a second X-ray beam that's going through 3 centimetres of dark and 1 centimetre of light, and then a third X-ray beam that's going through 4 centimetres of light grey. So what are those 2 different grey? Well, the dark shaded area is bone and the light shaded area is tissue. And the linear attenuation coefficient, so our mu values for the X-ray energy at 68 keV are 10 per centimetre and 1 per centimetre for bone and tissue respectively. So 10 per centimetre for bone and 1 per centimetre for tissue. And so if we're going to solve this problem, we're going to I've got old fluid mechanics sheets, you can kind of see through them. Doesn't matter, won't stop us. So we're going to need our equation for understanding how intensity moves through a material. So back in the lecture we said that Ix, so at some distance x, is equal to our initial intensity, I0, multiplied by a decay function that's relating our mu, our linear attenuation coefficient, to the distance that we've travelled through our material. And we also said, back in one of the slides, that if I've got different materials that I'm going through, I actually need to basically sum these terms. And so from multiple materials, this would become mu of material 1 through the distance plus mu of material 2 through the distance it's travelling. And so if we just break that out as a function, then we should get mu1 x1 multiplied by mu2 x2. Okay, so there's some high school maths right there. And so essentially if we're looking at this so this is just our general approach here. So if we look at X-ray beam 1, X-ray beam 1, then we can say, well, our intensity when we come out the back end of the beam, okay, at our film, is going to be equal to, let's call that I1, our initial intensity, I0, multiplied by the decay function of our material, which is bone, the dark shaded area, and we have, what did we say, 1 centimetre of that and 3 centimetres of the light shaded area. So I'm going to have minus mu for bone multiplied by 1 centimetre and the linear attenuation of our tissue multiplied by 3 centimetres. And we know what mu b is. That was given to us as 10 per centimetre. And we know what mu t is. That was given as 1 per centimetre. Yeah. And so then we can basically just calculate that and we should get 2.26 by 10 to the minus 6 multiplied by our initial intensity, which is not a value that they've given us in the problem. So if we do the same thing for the next two beams, I can calculate I2. And so this is going to be the initial intensity, and this time we're going through 3 centimetres of our dark shaded bone and only 1 centimetre of our tissue. So that'll be mu b times 3 and mu t times 1, and that gives us 3.44 by 10 to the minus 14 times our initial intensity. So you can see that we've got two different relationships to IO now. And then if I do the third beam, so this is my beam that's only going through 4 centimetres of our light tissue. So I3 is going to be I0. I've got no bone component, so it's just the tissue component times 4. And that should give me 0.018 I0. So that's the maths side of the problem. But what the heck, how do we interpret what we've just calculated? So what am I seeing? We've basically calculated the X-ray intensity as a function of I0 for each of these three beams. And we've said that with 1 centimetre of bone and 3 centimetres of tissue, I have 2 by 10 to the minus 6. With 3 centimetres in bone and 1 centimetre of tissue, I have 3 by 10 to the minus 14 times I0. And then for the last one, I've got an I3 of 0.018 I0. So more bone equals more attenuation. Yep, I would agree with that. So basically what we're saying is the bone attenuates a lot more of the intensity. So the bone doesn't let as much of our intensity through to the other side compared to our soft tissue. So even just a little bit more bone, so from no bone to 1 centimetre of bone, you can see that we've got quite a large change in how much of our intensity comes out the back end of our material. Yep, very good. And so if you go back to slide, I think it's about number 56. I'm looking at notes from last year, so I'm not 100% sure if I've got my slide numbers right. But basically we said, maybe it wasn't 56. Yeah, but we were looking at the difference between bone and fat and muscle, I think it was. And you could see at those lower energies that they've got very similar, so they've got very different attenuations. And that's really what's happening to our beam. So if we look at, are there any questions about number 3 before I move on? Otherwise, I'm going to scroll back. So now we're at the top of page 2. And the question is, explain why the attenuation of bone is much, much greater than the attenuation of tissue at a low X-ray energy. But the two values become closer as the X-ray energy increases. So does anyone want to hazard a guess? So I think earlier somebody said that we see a photoelectric effect at low energy. And so what does that mean in terms of our attenuation values? Exactly, yep. So greater energy is less prone to attenuation, as in it's harder to get it attenuated because, of course, you kind of, the energy is pushing the beam through the tissue more efficiently is one way to think of it. The thing that happens, though, is you increase your energy, then scattering starts to dominate. And if you remember that Compton scattering is completely independent of our effective atomic number of our tissue. So whether it's bone or muscle, it no longer matters because you've got all of that Compton scattering happening. And so now, as the energy increases, essentially those differences that you're seeing from the photoelectric effect disappear. Excellent. We're powering our way through this. I think it's very weird not having you guys in the same room, although it would be weird having you in my house. Okay, number 5. The linear attenuation coefficient of a gadolinium-based phosphor is used for detecting X-rays. Used for detection of X-rays is 560 per centimetre at an X-ray energy of 150 keV. So they're saying that the mu value, the attenuation coefficient of our detector material, our phosphor, is used when we're using an X-ray that has 150 keV, and it itself has a mu of 560 per centimetre. So you can see that's a much higher number than our bone and also a much, much higher number than our tissue. So we're not expecting a lot of X-rays to get through there, which is good because we want to use that to actually convert our X-rays to photons. So what percentage of X-rays are detected by phosphor layers of 100, 250 and 500 micrometer thickness? And so essentially we can do a very similar thing to what we did in question 3. We can calculate our intensity values coming out the other end of our phosphor layer. And so let me just bring this back down to the top. And so this is question 5. And so we've said that mu of phosphor, the question's given that to me as 560 per centimetre at 150 kiloelectron volts. And they're saying what percentage are detected? What percentage of my X-rays are detected? Okay, and because they're asking for a percentage, I don't actually need to know my initial intensity because I can calculate them in relation to each other. And so if we look at the phosphor layer that is, what was the first one, 100 micron thickness, so let's call that I100, then essentially we can say that that's related to my intensity multiplied by my mu, which is 560, by 100 micrometers, which would be 100 by 10 to the minus 4 per centimeters. And so that's going to give us a value of 0.0037 I naught, or if you think of that as a percentage, then that would basically be, you can bring that into decimal points, that would be 0.37% of I naught. So I've travelled, my I naught has come into my phosphor layer, and then after 100 micrometers, excuse me, this is now my I100. And so I had 100% here, and now at this end, I've only got 0.37% of my 100% left coming through 100 micrometers. So this is essentially the amount that has made it through. So 99.6 3% would have been absorbed by the phosphor layer within that 100 micron. So now if we do the same thing, looking at our 250 micrometer layer, so we'll just plug 250 by 10 to the 4 in there, then we're going to get a value that says we've got 8.32 by 10 to the minus 7 I0. So now we're getting basically, if we had 99.63%, now we're up to 99.9999% detected. Okay, so that's basically 0.0001 that have now made it through. So just by increasing our thickness from 100 to 250, we've been able to get a larger number of our X-rays detected by this phosphor layer. And then if we move it all the way up to 500, so we're now twice the thickness we just had, or 5 times our original thickness, then we're going to end up at basically 0. Nothing much is going to get through. If you plug that in, I0 by e to the minus 560 by 500 by 10 to the 4, negative 4, then basically you're going to get nothing. So therefore, essentially, we can say that everything was detected by our phosphor layer. All of our X-rays were absorbed and detected by our phosphor layer. So if you remember when we were talking about the thickness of a phosphor layer, essentially we said if I've got my I0 and it's coming through a phosphor layer and I increase that thickness, what were some of the pros and cons of increasing or decreasing the thickness? So a pro is clearly that the thicker it is, the more of my X-ray I can detect. What would be the con? Glow. I think you're talking about that phosphorus glow. Yep. There was another really important, expensive. Yep, you add some cost to it. I agree with that. But there was this particular thing that we said. So say I've got the conversion, and now it has to keep traveling through this thickness. Yes, less resolution. Yep, that's exactly the answer. So we've got this spread that happens, and we called that the light spread function. And so the more thickness that I have to travel in, the greater that spread is going to be. And so if I can keep it thinner, then I don't get as much light spread, which is good because then I've got a better resolution, as Mitchell says. But if I increase the thickness, then I can detect more of my X-ray. But then, of course, I've got a lower resolution. So this is one of those trade-off points. You can see, I mean, maybe 0.37% left over at the end is not too bad at all. So you can imagine that they're probably quite thin at the end of the day if resolution is important. Are there any questions for that? It's like speaking into a vacuum. Well, let me move to number, what are we up to? 6. So in figure 4, which is at the bottom right that you can see here, we have, it says calculate the relative intensities of the signals S1, S2 and S3 produced by each crystal. The value of our linear attenuation coefficient of our tissue is 0.5 per centimetre, of the bone is 1 per centimetre, and of the crystal is 2 per centimetre. So essentially what we have is our intensity coming in and then hitting our material and then going through this crystal. And you've got this signal coming out the back end, S1, S2, S3. You can see that essentially your crystal is present in all 3 scenarios. And so the crystal won't actually change the as in you'll get exactly the same loss of X-ray attenuation. You get the same X-ray attenuation in all three scenarios because that thickness 1 centimetre crystal hasn't changed. So essentially we can just calculate what that contribution is and we can understand what's going on there. Yeah, in relation to the larger question. So basically what we really want to find out is what is the what would you call it, the I naught of the crystal. So what's the intensity of my X-ray as it's about to hit my crystal? Because then that's going to tell me essentially what I need to know to answer this question. So let me just put some of that on paper for you, some of that thinking. So I've got my I naught coming into my material, whatever that is. And I've got my crystal in all three scenarios sitting here at the 1 centimetre from the end mark. And so this is my IX, but in all three cases, whatever my intensity here is, it's going to be reduced by the crystal the same amount after that point. So I could calculate this I naught of my crystal, so to speak, at this point here. So we can start by calculating I naught crystal. And so that's going to be whatever my IX coming out the back end here is going to be my I naught of my crystal multiplied by the decay function of my crystal attenuation, which was 2 per centimetre. So that's -2. And then multiplied by 1 centimetre, which is the distance that it travels through in all three cases. And so then that's going to give me a value of 0.135. So this is essentially my intensity of my, whatever the intensity was coming in here, it's lost just by going through the crystal, that what would it be, 86.5% of its intensity by going through the crystal. Does that make sense to everyone? So now what we really want to find then, in order to answer the question that's being asked, is what is this value for each of my three scenarios? So I'll put that together as three scenarios. So in the first scenario, my I naught at this point here where my crystal starts, that's going to be equal to my incident intensity multiplied by the, what have we got here? We've got 1 tissue, 1 bone. So 1 times tissue is 0.5. And then the bone is 1. And so then from there we can calculate a value of about 0.368 of our initial intensity. I can do the same for our second scenario, which has, oh, sorry, that was my second scenario. I'm going nuts. So that's the value. Okay, that's the answer to number 1, but let's get rid of that go there. We've got 2 centimetres. That's what I've done wrong. So then let me write this one out. Excuse me, I'm confused by my own problems. So now in the second scenario, I've got 1 centimetre of tissue and 1 of bone. So that's going to be the minus 0.5 times 1 and the 1 times 1. So that'll give me 0.223. Okay, so apologies for what's going on here. So that's a 2, that value there. We've gone through 2 centimetres of tissue, and tissue is 0.5. So that's minus 0.5 times 2. That's what belongs in that bracket there. And so then in the third scenario, we've just got the 1 centimetre of tissue, which you can see here. So then that's going to be my I naught E minus 0.5 times 1, and then there's no bone, so that gives me 0.607 times my initial intensity. And so if we're looking at this in terms of relative intensities, which is essentially what they're asking for, we know that each of them, whatever comes out after this value, we see another 86.5% loss of intensity, but essentially relative to each other for those three scenarios, we could say, for example, that the relationship between signal 1, so this one here, and signal 2 is basically the same as saying 0.368 over 0.223. And so that's going to give us about 1.65. So another way of saying that is signal 1 is 1.65 times more intense than signal 2. Okay, so you've got excuse me, you've got more of your X-ray that's made it through to your crystal. Less has been attenuated, and so at the point where it's about to go into the crystal, it's 1.6 times more intense, and after the crystal, they've both lost the same amount of intensity, which was 86.5%. We could do the same, for example, between our signal 3, which was just the 1 centimetre of tissue, compared to the signal 1, which had 2 centimetres as tissue. So that would be 0.607 divided by 0.368. And so that means that we're again about 1.65. So signal 3 is 1.65 times more intense than signal, 1. Okay, and then if we did signal 3 compared to signal 2, then what we would see is that we're basically about 2.7 times more intense. And so each time we add more thickness and more structure, different attenuating structures, then we change that. That seems pretty straightforward. I feel like a lot of the X-ray questions just keep working off the same equation, main equation, which is pretty much the only equation I think in the lecture slides for X-ray. Okay, so it's 5 o'clock and I've got 2 questions left, so I reckon I can scoot through these without too much drama. So number 7, are there any questions about any of the questions that I've had so far before I move on? I've still got people in the room, I do. Haven't scared anyone off yet. So essentially, number 7 is saying, I've got an X-ray with an energy of 60 kiloelectron volts that strikes a gadolinium-based intensifying screen that produces photons at a wavelength of 450 nanometers. So essentially, I've got this phosphor screen that converts my X-ray into photons so that I can detect them with visible light. So I'm now shifting down my electromagnetic spectrum. And the energy conversion coefficient for this process is 20%. So they're asking how many photons are produced for each incident X-ray, and then it gives me Planck's constant, and it tells me that 1 EV is 1.602 10 to the minus 19 joules. And so the question's essentially asking how many photons per incident X-ray. Let me write that down for us. Okay. And it said that I'm given 60 kiloelectron volts of energy, and I'm converting these to a wavelength of 415 nanometers for my photons. That's my wavelength of my photons. Okay. So I've got my intensifying screen here, and it's getting hit with 60 keV, and it's converting these guys to photons, and it's basically got a conversion efficiency of 20%. So it's telling me that at this end, I've got 0.2 times 60 keV that have been converted to photons. That's what that statement is saying. And so essentially, another way of saying that is I've got 12 keV, so 0.2 times 60, worth of photons that have been converted. So then the question is, essentially, how many photons is that? And the problem kind of helps us out because it talks about Planck's constant. And so if we head over to our lecture slides, we'll find, it was one of our early lecture slides, that there is a energy per photon for any light that's equal to our Planck's constant, our speed of light, and our wavelength of our light, right? And so we know that Planck's constant is 6.63 by 10 to the minus 34, because the problem's given us that info, or we've managed to memorize that. And we've got the speed of light, which it hasn't given us, but the internet can help us out with that. So I think that's around about, I'm going to say 299.8 by 10 to the 6 meters per second. And this guy here is being measured in joules seconds. And then all of that is divided by the wavelength of light, which was given as 415 nanometers, or 415 by 10 to the minus 9 meters. And so from there, we should be able to calculate that the energy per photon is going to be 4.79 by 10 to the minus 19 joules. And then if I've got 12 kilo electron volts of photons, then essentially I can calculate that what were we given? We were told that 1 electron volt is basically 1.602 by 10 to the minus 19 joules per electron volt. And so we can basically calculate that I'm going to have 2.99 electron volts per photon emitted. And so I know how many kilo electron volts I had. So that basically all we're doing here is we're converting to electron volts. Okay. And so if I've got 12 keV, then I can say, well, 12 by 10 to the 3 divided by 2.99 per electron means that I'm going to have about 4,000 photons involved in this incident energy beam per incident X-ray. So are there any questions to that? I feel like I'm moving fast, but I think part of that is that I don't have you guys in the room talking at me. Like I said, I'll put all the solutions online as well. But if you've got questions, just shoot me an email and I'll have another go at explaining myself. So the last question we have is actually related to the idea of digital subtraction. So we looked towards one of the last slides about the idea of being able to get an X-ray at a particular energy that might be ideal for the soft tissues, and then another X-ray for the harder tissues, and then we could subtract them from each other in order to kind of pull out the structure that's interesting to us. And so the last question says, in digital subtraction angiography, essentially you've got two images that are required, and in this case you've got them before and after a contrast agent. So instead of playing with the energy, we're playing with the addition of contrast agent. And so they want us to write an expression for the intensity in the first scan in terms of our incident energy, our attenuation coefficients of tissue and blood, as well as the distance through the tissue and the distance through the vessel that we're traveling. And so X tissue and X vessel are the dimensions of the tissue and the vessel in the direction of propagation. So essentially what they're saying is, I've got my incident energy coming through, and I've got some XT of tissue that it's traveling through, tissue, and then I've got some XV, which is the vessel that it's traveling through, and then I've got whatever comes out the other side, so my I. And so I'm going to have two images. I'm going to have I1 and I'm going to have I2. So let's focus on the first one, the first scan. In this case, my tissue has mu T, my vessel has mu, what did they call it? Mu blood. Blood. There we go. Okay. And so we can write that expression, because we've been writing it all afternoon at this point. The intensity coming out is going to be equal to the intensity coming in multiplied by the decay function for minus mu T x T multiplied by the decay function for mu B x V. Okay, so just what we've been doing for the last hour, pretty much. So that's the answer to part A. The next part says, well, now write the same expression, but this time for the second scan, where instead of having the attenuation of blood, I've now got the attenuation of my contrast. So or my contrast, as the question says. So I've now replaced the blood with the contrast agent, so I'm going to have a different attenuation coefficient for that. And so for the second scan, it's going to be the same tissue decay, mu T xt, but then over here we're going to have the mu of our contrast agent multiplied by the distance xv travel through. So the contrast is going through the vessel, it's not in the tissue itself. So that was two parts of the question that's fairly easy. So now the third part of the question says, is the image signal intensity from static tissue removed just by subtracting these two images? So it's asking me, if I say I2 minus I1, is that enough to remove this part of my signal? Anyone want to throw an answer at me? No one? You've all fallen asleep? I feel like it's fairly, why would they ask this question and then have a part D, right? Okay, well, let's give it a go. If I actually do this, if I say I2 minus I1, then I'm basically going to be left with my mu T xt, which is common to both, and then I'll have my mu B xv minus my mu C xv. Okay, so essentially it's pretty damn obvious when you look at it like that. Have I gotten rid of this guy? No, I haven't. Sorry, this one here. Okay, it's still there. It's not been removed from the signal that I'm collecting. So then that brings us to the last part, which is essentially show that the signal from the static tissue is removed if I compute log I2 minus log I1. So we're saying log of I2 minus the log of I1. And if we play this out, we can show then that we get log of I0 minus mu t. Let's just do is log of I1 is mu t xt minus mu b xb. Log of I2, similarly, am I still on the page? Yes, is mu t xt minus mu c xb, and then I can set I2 minus I1, and we're going to be left with essentially these guys cancel out, and we should have minus xv, and then mu c minus mu b. And so we've managed to get rid of that mu t xt component. So essentially we can say the static tissue effect, I'm missing the letter, is gone. Okay. Are there any questions for me? For the record, I have never squeezed that tutorial into one lecture before, and we have done it with 3 minutes to spare. So that is impressive. I think part of it is that you guys are a lot quieter than you usually are. Otherwise, with that, I am going to call it a night, and thanks again for logging in and joining me. I will be back on Wednesday for our Wednesday afternoon lecture. I will upload the CT notes before then so that you've got access and can have a look. But like I said before, if you've got any questions about anything that we did today, please have a go, have a look, send me your questions, and I can't promise I'll be a quick responder, but I will do my best to respond ASAP. Otherwise, have yourselves a great evening, and I will see you on Wednesday, or not see you, sort of see you.